Hey everyone, I wanted to do a faster version of how to read a pressure enthalpy graph. Keep in mind, when we have a single component, such as we have here with the refrigerant Opteon, that means that knowing any two uh, uh, state functions, such as enthalpy, which is on the x-axis, and pressure, which is on the y-axis, means we have specified all of the other state functions as well. So if we pick some point, say out here, um, we can clearly know the enthalpy associated with that point by reading where it falls on the x-axis. And we can clearly understand the pressure at that point by seeing where it falls on the y-axis. But we can also find out where it falls with regard to every other state function, which includes temperature and entropy. Wow. So all of this stuff is captured right here. So let's make sure we understand where we can get all of those things from. So let's start with the simple ones. I just put a kind of random spot out here, and I'm going to see that if I drop down a vertical line from that, our enthalpy value is just a hair over 120 BTU per pounds mass. And then we want to see what pressure we are talking about at the center of this point. I draw a line out to over here, and I can now see that's just a hair under 80, okay? 80 PSI. So what else can we learn from what we have here? So now this gets a little bit trickier. We have to pay attention, and this graph nicely has things in other colors. These values that I'm circling are our entropy values, and they're in BTU per pounds mass Rankine, and they tilt the isoentropy lines, isentropic lines, tilt as I'm kind of drawing them here, fell off that line. And so to find out the value for entropy at the point I've circled, we look for the closest isentropic line, and I picked something that falls right on one, but we might otherwise have to interpolate. So this is our value for entropy. So if we wanted to change in a reversible system, we would slide up and down this bright green line. Now the final line that's on here that we're really going to care about a lot is the temperature. And so the isotherms are kind of swoopy. So the isotherms travel from the liquid side to the vapor side through the phase envelope. So the easiest place to find them, of course, is in the phase envelope itself. I'm going to trace one of these in yellow. So for example, if we were to look at the 50 Fahrenheit line, here it is in the phase envelope. And then when it gets to the saturated liquid edge, that temperature line, where are we going to follow it? We have to look very carefully. It's kind of dark blue on this. It goes pretty much straight up. And then if we're going to follow it on the saturated, after it hits the saturated vapor side, it goes not quite straight down. You see that now? So if we want to find the temperature of that pink point I circled to begin with, we've got to find its isotherm line, and it looks like it's right here on the 110-degree line. And so out here on this point, we're at 110 degrees. And if we were going to bring that in through a condenser, for example, at constant pressure, it would end up condensing at, what did we have here? It would travel this way. And so it would end up condensing at around 30 degrees. All right, that's all the lines. And this general setup works for any pH diagram you might encounter. So Enthalpy doesn't have to be in BTUs per pounds mass. It may be, for example, in kilojoules per kilogram. Pressure doesn't have to be in PSI. Pressure could be, for example, in bar, sometimes in atmospheres, something like that. But they will always have this collection of different values, and it will, in general, have this shape. Something I want to additionally point out is why, in this day and age, use a graph when we have modeling systems that can give us precise numbers. And it is true, I encourage you to use a model or a simulation package or an equation of state to get really precise values for enthalpy and entropy if you are in fact designing a refrigeration system or a heat pump. But what the graph gives us that the precise values don't is the ability to look at this and have a sense of the choices and the trade-offs that you are making. So you can see, for example, readily and compare, gee, what happens if I need my high temperature in the condenser to be something more like 90 degrees Fahrenheit? What other choices do I need to make if I need my freezer to run at -50? Um, and what can I do perhaps to minimize the amount of work that I need the compressor to do? Are there places along this curve where that is the saturated vapor curve where I could get more bang for my buck or not? And I want to add one small thing that I realize I omitted because I don't happen to use this, but I do want to call your attention to the fact that I'm going to highlight this. Volume is also captured on this graph. So if you need the specific volume or density, just flip it over of this, you can also find it here. And that's going to be useful in your design if you want to figure out how big your pipe's got to be. Thanks.